Hello.
Good afternoon, everyone. That seems loud, but okay. Welcome to the near end of our science speaker series for this semester. Next week, we will have two events, Tuesday and Wednesday, where our graduating seniors will all tell us about the research they've been doing for their capstones. But this week, we have our own Dr. Bailey giving a talk. Dr. Bailey got his PhD from Indiana University and then came to Embry-Riddle in 2007 as an assistant professor. He's now a full professor of physics and is reporting on what he's been working on lately, especially with his recent sabbatical that he had last fall. And so today, Dr. Bailey is going to tell us about research on tests of general relativity from laboratories to astrophysics. So thank you, Dr. Bailey.
Thank you. Thank you, Eric, for help. So I'm going to give an overview of some of the research I work on, and I'll mention at least one recent project I did with some undergraduate students. But I will spend probably 40 or 50% of the talk just doing background on what is relativity. Not everybody knows in the audience. So I'll spend some time with that. You see in this picture here, I just picked a couple of different systems, if you will, when you can do experiments testing gravity. I'll talk about short-range gravity test that looks something like this. This is an experiment from China. And then this, everybody's seen the colliding black holes and neutron stars, this picture of waves coming out, gravitational waves. And then perhaps not everyone is as familiar with precision solar system tests of gravity, so I'll mention at least some of that. Okay, so first some acknowledgements. So I've been supported by Embry-Riddle and the NSF, that's several NSF grants, and I've been supported by the institution I got my PhD from, Indiana University. They have a Center for Space-Time Symmetries, that's what the IUCSS is. And I've been supported by some colleagues in France. I've done a couple of visits there, and CNRS is their umbrella institution. I have collaborators here at Embry-Riddle, so I want to highlight graduate student Kelly, who's about to graduate, and some undergraduates, so Janessa and Alex and Haley. They're working on some different projects. I'll probably won't get to talk about all those projects, but that's ongoing. I've had some undergraduate students in the past. Just want to highlight some of them. Rondale So, who's now at postdoc at Illinois, Urbana-Champaign. And Daniel Havert is doing a PhD in biophysics at IU. And Jennifer James is currently a graduate student at Vanderbilt University. And there was just a news article. So. I have other collaborators around the world. Kostelecki, who was my PhD advisor, and Jay Tassin at Carleton, Muse at Cal Poly, and many others. And then I collaborate with people at the Paris Observatory, and in particular, recently I've been collaborating with Li-Jing Xiao and his group at Peking University. Okay, so what are we going to talk about? So first, I'm going to try to give a background on special and general relativity, just a kind of an overview of what those ideas are, try to give you an idea with as little equations as possible. And then I'll talk about for motivation for tests. Why are we so interested in testing special and general relativity? You hear that these are very good theories that work very well, so why are we trying so hard to find deviations? And I'll talk about how we describe that. What does it mean to have a breaking of special relativity or breaking of general relativity, which we call Lorentz violations. And I'll talk about a theoretical framework that we've been using called the Standard Model Extension Framework for studying these tests. And I won't have time to go through all the tests there are. There's so many. I'll just talk about 3, maybe 2, depending on time. So one thing I did want to highlight, and one of my favorite tests, is lunar laser ranging. It's so close to the Earth, it's almost like a laboratory, and the precision that they can measure the distance from the Earth to the moon is pretty astounding. So I'd like to highlight that one. You don't hear about it a lot. And I'll talk about short-range gravity tests in the laboratory on the Earth. And then, if I have time, what we can do with gravitational waves. So the first thing is, let's go back and talk about special relativity. What is it? So there was a famous paper written by Einstein in 1905. This is the title here in German, and then this is the translation on the electrodynamics of moving bodies. And that established 2 postulates of special relativity. First one is that the laws of physics are the same to all inertial observers. Now, if you don't know what an inertial observer is, that's a whole nother lecture. But basically, you can think of it as a non-accelerating, non-rotating observer. So you're not in the Gravitron ride at the amusement park. That would not be an inertial observer. So this principle was already known to Galileo and Newton. However, what was different for Einstein was the postulate that the speed of light, speed of electromagnetic waves, is measured to be the same thing, same value to all inertial observers. So this, at the time when it came out, was radically new, because physicists thought Newton's laws were it, and that it was electromagnetic theory that needed modified, but in fact it was electromagnetic theory was correct, but all observers actually measure the same speed of light. So this gives a departure from Newton's mechanics, at least for speeds close to light. So what are the consequences of this? So we have, I'll go through a couple of examples here because they're pretty intriguing. It's what got me into this subject. So consequences of special relativity is that when we relate 2 different reference frames moving relative to one another or rotated relative to one another, we have to do a different kind of transformation that mixes space and time. And so you can think of it as kind of a rotation. So here's a rotation of space. You take your XY axes and rotate them by some angle. And so that's called that's a rotation. But Lorentz transformation, or Lorentz boost transformation as we call it, is a kind of rotation in a time and space picture here. So the time and space axes become tilted towards one another. So it's not exactly a rotation, but it's kind of like a rotation of space and time. So this is when you go from one coordinate system t and x to a moving one, t prime, x prime. So that's what it looks like. So this has a lot of consequences to measurements, particularly for objects moving close to the speed of light relative to the observer. And notions that were, a lot of notions that were in physics, like absolute time, those disappear here. So you get a lot of interesting phenomena: length, contraction, time, dilation. The idea of two events being simultaneous is relative. And drawn this little sketch here showing if you have two sets of rods and clocks, and you have one of them moving at velocity v relative to this one, then the ticking rate of the clock will change and the length of the rod will appear to be contracted in the direction of motion. Here's another famous consequence, which can be, this is called the twin paradox. It's not really a paradox, but it's often posed that way. So you have two twins on Earth, the same age, and one of them gets into the rocket, goes on a trip, traveling close to the speed of light, comes back, and finds that the Earth twin has aged, let's say, 40 years, while the space-traveling twin only aged 20 years. So this is a real effect of special relativity, and if we ever make rockets that can travel that fast, we'll have to deal with that. Okay, so to get into a little more detail, the laws of special relativity are described by assuming what's called perfect Lorentz symmetry for all different kinds of matter, anything you do experiments with. There are two different kinds of transformations. There are rotations. So most of you are probably familiar with the idea of a rotation around x, y, or z. So here I take the Embry-Riddle eagle. It's rotated about some axis by 90 degrees. Then there's boosts. Those are taking an object and then giving it a constant velocity in some direction. And so here the eagle gets boosted, is now traveling at speed v, and may appear contracted like this along the direction of motion. There's 3 different ways that you can do this and 3 different rotations. There's 6 altogether symmetry transformations. So the statement of special relativity is that you do an experiment, and then if you rotate or boost your apparatus, you should have the same experimental outcome. So that's kind of schematically illustrated here with these 2 stick figures doing an experiment. So the outcome should not depend on orientation and boost. And there's other kinds of space-time transformations. And I want to point out here, if you take the Embry-Riddle eagle and do a parity transformation, which is a mirror reflection, apparently you get an American eagle. Okay, so what is general relativity? Well, as the name says, it's more general. Okay. So the idea is, in 1915, Einstein wrote a paper describing the theory of general relativity, which can be nicely summarized in terms of this kind of rubber sheet analogy here. But basically, space acts on matter, causing it to move along a curved path, and then in turn, matter reacts back on space by curving it. So this little figure kind of illustrates that. So you have a big mass here. It's curving the space around it. So a smaller mass will tend to move on a curved trajectory, like an orbit, for example. And then wherever you have a mass, there's a slight curvature of space-time in that region. So if you had to summarize general relativity in one sentence, it would be that one. Okay, so let's talk about some of the consequences of general relativity. I should say today, general relativity is our best theory of gravity, very, very well tested. It contains Newton's law of universal gravitation, which is the inverse square law. 2 masses attract according to the inverse square of their distance. And so that's a certain limit of general relativity. But other interesting things happen. with this curved space-time picture. So special relativity is within general relativity. It's a local thing. So if you're in a spaceship traveling somewhere in space, in your space capsule, laws of physics will appear as special relativity. But if you look over larger distances, you can see the effects of curved space-time. So here's an example, a couple of examples. As soon as general relativity came out, physicists were looking for verifications. And these are some classic predictions and tests of general relativity. So of course, the general relativity accounts for an extra precession of the perihelion of the planets. So those are orbital elements that describe ellipses. And so you see this precession, so the ellipse actually rotates. That's the effect. That was observed long before Einstein. There are huge contributions from Newtonian physics, but there was an anomalous extra piece to that was not explainable until general relativity. So I say extra precession. And that affects other things with the planets as well. Bending of distant starlight, classic prediction, observed first by Eddington in 1919, and many subsequent observations. And I have this little figure here to show you that this is a star, and it's going to pass near these two reference stars circled in red. And so what happens is you can watch the position of this star shift. This one's kind of far away, so it's not going to move much, but this one's going to move as soon as that mass comes near it. So you see it appears to have moved a little bit, and then as the star passes, goes back to its original position. So that's how you would observe the bending of starlight. There's all kinds of technical complications, like usually the star is emitting electromagnetic waves in many areas of the spectrum, and you gotta block those out sometimes. But that's the idea. That's what you would observe. There are other tests, maybe less well known, gravitational redshift, the idea that clocks near a big mass will tick slower. That was verified quite well in the 1960s. And then a time delay of light. So not only do you get a bending of distant light, it's also delayed in its arrival time. What does this have to do with reality? That's a good question. So here is my favorite example, general relativity in everyday life. We have some excellent navigation technology, the GPS Global Positioning System satellites, which are roughly at twice the Earth's radius in orbit here, in roughly circular orbits. And so these all have precise clocks on them. And because of general relativity, the clocks on the Earth are a little bit slower than clocks on the satellites by about 38 microseconds per day. And so if you want accurate navigation, you actually have to have a precision of something like 50 nanoseconds per day. So you need to make sure you include this drift here. So you have to use general relativity for precise GPS navigation. By the way, you might think the satellites are moving faster than objects on Earth, so you might think, if you know anything about special relativity, oh, they should be ticking slower. But in fact, there's a gravitational redshift that far outweighs the special relativity effect, 45 versus 7 microseconds per day. And so you end up with 38. Okay. What else? Other predictions of general relativity. Well, we have black holes. Everybody's heard of those, so that was a solution to the Einstein field equations. And there's observational evidence for black holes now, a lot of it. The whole theory of modern cosmology is based on a solution for the entire universe, evolving it backward in time. So that's based on general relativity. And of course, gravitational waves, which we know a lot about here at Embry-Riddle because we have faculty working on that. So a gravitational wave comes by and would cause a ring of masses to, for example, move in this manner. So space is stretching and expanding. But there's actually a lot of other tests of general relativity that you don't always hear about. I'll go into one of them. It's called lunar laser ranging, which is pretty interesting. And you can do a lot of ground-based experiments as well. And then, of course, you have other astrophysical tests looking at binary pulsar systems. And then, of course, gravitational waves. And we have 3 faculty on the LIGO collaboration. Oh, I forgot to put that one. There's the signal, first signal for gravitational waves from black hole binary in spiral, published in 2016, and there's a Nobel Prize. Okay, this looks really good. General relativity helps us with GPS and all sorts of stuff like that. Why do we think that something might be awry here? Well, there's a puzzle in physics that has not really been solved yet. So if you take general relativity, that describes gravity. So that describes the effects of gravity on sort of larger scales. On the microscopic side, if you will, is a standard model of particle physics, which describes 3 other forces: strong, weak, and electromagnetic forces. And that's described with particle physics. You have all different kinds of fundamental particles. I'm not really going to go into that. But it's a very robust theory, the best thing we have to describe fundamental physics on small scales. And behind that is quantum mechanics. And the issue is, if you try to apply the same techniques you do here with quantum mechanics, if you try to apply that to general relativity, you get divergent terms when you do the calculations and things like that that we haven't quite explained yet. So physicists think that there is some fundamental unified theory that combines these two, and by conventional wisdom, that would be valid at some very high energy scale, which we call the Planck energy. And so this is this says 10 to the 19 GeV for comparison. The Large Hadron Collider energy scales are about like 7 TeV or 7,000 GeV, so many, many, many orders of magnitude away. So we're not going to probe the fundamental theory by smashing particles together. So what else can we do? We can look at things in the following way. We have some fundamental unified theory of physics up here, some very high energy scale. We don't know what it is yet. It could be strings, it could be some other ideas, quantum gravity ideas that are out there. There's a lot of stuff. Thousands and thousands of papers, speculative papers. And so we don't know for sure. However, the things we do experiments with are like down at this level. We can do experiments with gravity. We can do experiments with different kinds of matter. And so what might happen is that some core principle in general relativity in the standard model could be broken by some unknown mechanism. But there's actually many different ways that that can happen, where you could actually come in and have a tiny, minuscule breaking of Lorentz symmetry for within general relativity in the standard model, and you could then, so you'd have tiny little defects here, and you could then try to observe those. So there's probably a lot more than this. There's probably thousands of papers. There's different ways for this to happen. Something called spontaneous Lorentz symmetry breaking is my favorite. I won't go into all of this, but there are many different ways that this can happen. It doesn't have to happen, but it's a very interesting possibility, and so it motivates experiments. So again, what you would hope to measure are minuscule deviations in observable physics, and then if you see that, then you have something new. Okay, a definite Nobel Prize there. So far, nothing new has been observed. How do we describe this? So This is how we describe a breaking of Lorentz symmetry. If you rotate or boost your experiments, the physics changes. Remember I showed you that little cartoon before. Physics is not supposed to change if you just rotate or boost your experiments. So the key thing is that it does change. And it turns out that any form of Lorentz violation you can try to write down can be described by what's called a background field. And so you have empty space here. Imagine that empty space is filled with some kind of background field. So it could be a vector like this. And what that represents is that there's a field that can interact with the matter you're using in your experiment. So there's not actually giant red arrows in space. That's just a visualization that we do. So let me show you more clearly how this happens. So here is an animation of the rods and clocks I showed you before, but now they have different colors. That means they're made of different materials. So we have two different sets of rods and clocks. And really the only way to measure the basic relativity principles is to use different rods and clocks here, because principles of relativity said it doesn't matter which kind of rod or clock you use. So I have two of them there. Now you rotate them around, nothing changes. Ticking rate stays the same, length stays the same. Okay, let's look at the Lorentz violating case. Now you have a background. And now what could happen is this background field could couple with the matter in these clocks in different ways, so that they have ticking rates that are different from each other and lengths that are different from each other. So that's how you would observe it. You take one set of measuring instruments and compare it against another. And yes, this does look like the Twilight Zone intro, if you've ever seen that. There's the clock. Okay, so how do we describe this? So we use a general framework, theoretical framework. I'm not going to go into all the theory behind this. I'll just describe it at its pictorial level. So you have, this was actually developed by several physicists back in the 1990s and 2000s. It's called the standard model extension. The idea is you take your known theories that work very well. We don't want to throw them away and start from scratch. We take them, we keep them, and we add to those theories all possible forms of symmetry breaking with these background fields. And there's a mathematical way to do that systematically. So technical details. The standard model extension is what we call an effective field theory with a general Lagrangian. If you don't know what that is, just keep this picture in mind. It has all known physics plus minuscule Lorentz violating terms that we can use to do calculations and figure out what experiment is going to see what. This is the simple form of one such expansion. Okay, that's enough of that. So just to point out, let me just point out here that this is area has had kind of a boost of interest in the last 20 years or so. There's many experimental papers published. Actually, there's probably like 300 or 400 papers. This is a little outdated. Those are experiments reporting results in this framework. Experiments with all kinds of different things. And many thousands of papers published on different aspects of the SME framework. We've had major conferences, many experimental groups worldwide are working on it, and then we have this dedicated center, IU Center for Space-Time Symmetries. And there's been popular articles on this over the years. And so far, Einstein is correct. So I want to make sure that's clear. Not claiming any new results here. Let's look at the gravity sector. Focus on gravity. You have general relativity, and you add to that all possible Lorentz violation terms. So there's a complicated equation it leads to modified Einstein field equations, which I won't show you because most of you aren't familiar with that. How do we describe a deviation from perfect Lorentz symmetry for gravity? Well, it turns out one subset of the description, we can organize all of the quantities that describe the Lorentz violation into a 4x4 matrix. Now, I think most people in the audience have seen matrices before. So in the gravity sector, it turns out to be this matrix of coefficients that we call S bar. Don't worry so much about the mu and nu. Just focus on this, that it's a 4x4 matrix of quantities, symmetric. So these quantities here are unknown. They start off as unknown. What are they? We have to go measure them. If Einstein was right, they are all exactly 0. Okay, so if any one of these is measured not to be 0, with a statistically significant measurement, we have a breakthrough. But that has not happened yet, and may never happen. So these are the quantities to hunt in experiments. So I'll show you an example that I think would be understandable to many undergraduates, and that's you learn about Newton's inverse square law of gravitation. That is the first term in this equation, minus g times the two masses over r squared, times r hat. So it points between the two masses. It's attractive. The other two terms in this expression are the corrections that you find from this matrix here. And so you have this is actually a 3x3 matrix dotted into the unit vector r hat, and this is another combination here. So you get these extra terms in the gravitational force between two masses. What would that do? So here's the gravitational field around the Earth. It's nice and spherically symmetric. Maybe not exactly, but we'll pretend. When you turn on these S bar coefficients, it would become slightly asymmetric here, shown in an exaggerated form. So you could hope to measure those things by studying orbits. And so we come to the first experiment, lunar laser ranging. Okay. I like to highlight this one because it's not often, a lot of physicists don't know much about it. We are fortunate that the Apollo astronauts left a bunch of, they're called retroreflectors on the moon in these 4 sites, and then there are 2 Russian missions that left also reflectors. So what we can do is bounce laser pulses off of those reflectors and then try to measure the returning photons. And it really ends up being like a photon count. Try to get the most photons counted. So there was a telescope in Texas that was doing this, and then more recently at Apache Point Observatory in New Mexico, a more powerful laser and a better collector and so on. So the idea is just to measure this R by measuring the light travel time, and it can be measured very precisely. Less than 1 millimeter precision. Okay, so you can measure this distance to less than 1 millimeter. Of course, that distance changes like crazy because of all sorts of tidal effects, but you can measure changes in that distance to less than 1 millimeter. So what would Lorentz violation do? This is a highly exaggerated depiction. We have a background field, that's these red arrows, and then we have the moon going around the Earth, and the light gray orbit would be the usual orbit, and yeah, there we go. The animation shows a weird kind of delayed path in a couple spots for the moon. So that's an exaggerated depiction of what this effect would do to the moon's orbit. So it slow it down in some spots and speed it up in other spots. So some folks that have access to this data, some of them even controlling some of these telescopes, have done an analysis. This just shows you a historical accuracy of lunar laser ranging data since around 1970. So they have, so this is centimeters. So that's, you can think of that as roughly the precision. So here they're measuring precision to 30 or so centimeters, and then it has successively improved down to, it's still centimeters here, but that's over almost 20 years ago. So I don't have the latest graph. The Apollo project in New Mexico achieves even better sensitivity. And 2 groups have published constraints on that matrix of coefficients, the S-bar terms. They constrained 6 of them. These have no units. So you can see how well Lorentz symmetry is tested. The constraints are of order 10 to the minus 8 or 10 to the minus 12. So that's 1 part in a trillion. So general relativity appears to hold to that level. Okay, so that's lunar laser ranging. Let's look at another test. So we don't often hear about laboratory tests here, so I want to point some out. So these are called short-range gravity tests. So the idea is to try to make sure that Newton's inverse square law of gravity holds at very small scales. It turns out there was a gap of data in this area, and physicists became interested 40, 50 years ago in trying to find out, does Newton's inverse square law hold at millimeters, micrometers, at those kinds of scales. At the same time, theorists proposed that there could be new forces that are confined to short distances. Sometimes they were called fifth forces, and perhaps a little more famously, in the late 90s, some physicists proposed that gravity actually acts in 6 dimensions. There's 2 extra space dimensions that are really small, and those could affect Newton's law of gravitation on small length scales. So they came up with these parameterizations for new effects. So basically, this is the potential energy between 2 masses. In physics 2, we know that goes like g(mm) over r minus g(mm) over r. And so that would be the 1 in this expression, and then this is the extra term, alpha times e to the minus r over lambda. So you get this exponential term. As r becomes large, this goes away, so it only acts at short distances. And you have 2 parameters. You got alpha and lambda. Alpha tells you the strength of the new force. Lambda tells you the distance scale that it acts at. And the physicists have proposed other forms of new potentials. This one is just a power law in the distance r. So you could have, instead of the inverse square law, you could have an inverse quartic law. So you could have corrections. None of those have been observed, but you can place constraints, and they're still looking. These are sample experiments that try to test Newton's inverse square law with laboratory masses. They're very, very hard to do because the Earth's gravity dominates everything. You want to subtract that out and measure the force between 2 laboratory masses. So there's all different designs for this. This one is a lot of them are torsion pendulum experiments. This one, basically, they're trying to measure the force between this arm here on a pendulum, and this one is fixed in the laboratory. So they oscillate them or do all kinds of tricks, and there's all sorts of extra equipment needed to just try to optimize that signal. It's very hard to measure. You have these cantilever experiments as well. We have 2 flat plates, and you're trying to measure the force between those 2 flat plates. And then here's a sphere and a flat plate. These are very small experiments here. And then University of Washington group devised a torsion pendulum with these discs here with holes in them to simulate the absence of mass there. And they twist this thing at some frequency and try to measure the force between this plate and the bottom plate. You can ask one now. Very, very good question. So you can actually write down. So there would be. This is Newtonian level. So you'd have to add general relativity corrections to this. And my understanding is that they can be calculated to have a number for that, and they're very small, so they wouldn't be detectable. In fact, some of these experiments can't even detect these really small ones. They can't detect the Newtonian force because their precision is not that good. Instead, they just look for gigantic forces on small scales. So yeah, basically it's too small to be measured, is my understanding. Okay, so let me talk about, finally get to some results from recent work that I did with some students. And so this one is a little messy with equations. I'll try to explain some of it. So this one's probably the most complicated. This is a tensor field equation. Basically what this says is G is curvature and T is matter. And so curvature is proportional to the presence of matter, just like that rubber sheet picture I showed you earlier. That's the idea. And this delta M term is an extra term coming from Lorentz violation. So basically you have general relativity plus an extra term. So I had some students work on this. Actually, Janessa Sloan was working on taking this equation and turning it into equations we could solve with differential equation techniques. And so in a special limit where everything's static and you just have mass density rho, you can solve for the potentials. This H00 is basically the Newtonian potential from a mass. And you have del squared, that's the Laplacian. Some of you have had vector calculus, you know what a Laplacian is. You have del to the fourth, it's Laplacian squared. So this is actually a set of coupled partial differential equations that are hard to solve. However, we do have an exact solution. We were able to get an exact solution. But you don't typically learn about these equations with these higher terms of 4 derivatives in your differential equations course. So that was new here. So Jennifer James, who just graduated last year, helped me with this calculation of solving this equation. And the answer is actually, you get, this is basically the solution. You get a 1 over r term, that's the Newtonian term, and then you get plus an extra correction term. And that has an exponential, kind of like that Yukawa potential I showed you. But it has other stuff that's not in the standard parameterization. It has this oscillation behavior, cosine of r over lambda. So r is just the distance between the masses. And lambda 1 and lambda 2 are 2 length scales. So instead of 1 length scale, you get 2. And then this term here, with this 1 plus 2 chi, 1 plus 4 chi. Chi is a dimensionless number, depends on these quantities k1, k2, and k3, which show up in the equations. Those are to be measured. We have to measure them. We don't know what they are. But this term could be really big and make a really big force on small distance scales. That's the point. So we published this in Classical and Quantum Gravity. It came out in the fall and then published earlier this year. So we're trying to twist arms and get some experimentalists to analyze their experiments to measure these quantities K1, K2, and K3. What would this do to an experiment? So we did some calculations with a flat sheet of or flat disk of mass, sort of thing you do in classical mechanics, I think. You find the gravitational field above a flat disk of mass. It was some in like cylindrical coordinates or whatever you want. So we want to know what's the gravitational acceleration here? How does it depend on the distance above the plate? And so we plotted a special case of that solution. And again, there's two different length scales, lambda 1 and lambda 2, which in this case just depend on one parameter, k, which we just call k. And this is basically a plot of the gravitational acceleration above the plate versus the distance. So, good. I don't know what that was. So you have G versus Z, and you vary Z and try to see what the effect is. This is what these experiments measure. The purple, it's a little hard to see, but the purple triangle is going across here. It's just a horizontal line at -1. That's the solution according to Newton. All of the other lines are different kinds of solutions due to Lorentz violation, and they have oscillations and going in different directions here, but basically you find the gravitational acceleration would oscillate in some way above the plate, which is has not been observed yet. But all of the effects are confined to a small region here, and really the experiments have to look for this and find out the value of these, like this K2 parameter, for example. But they could do that, and we came up with just a crude estimate of what they could measure. So assuming they don't see anything, they just basically see this purple line, they don't see any of these oscillations, then they can place a bound on any possible Lorentz violations. So this K2 parameter, like square root of K2 is less than 200 micrometers, which tells us that K is less than 10 to the minus 8 meters squared. Now it's in meters, and basically meters squared, so it's basically telling you the scale at which Lorentz violation could take effect. So we want to find out, is it there at some scale, or can we place a bound on it? How small? What's the upper limit on that length scale? Okay, how much time do we have? When am I supposed to be done? I'm past 1. 5? Okay. All right, I'll just do a little bit on gravitational wave tests. Just a quick summary. Gravitational waves propagate in vacuum. The observable effects are kind of a stretching and squeezing of space-time. In general relativity, there's two polarizations called plus and cross. And so here's a depiction of them here. This is two different effects that you see, or you see a combination of them. And we have large interferometers to try to measure that. And this was the first discovery was in 2016. So that's a very, very brief review of gravitational waves. So you could ask the question, what can we do with gravitational waves to test Lorentz symmetry? Well, I'll point out one example. So, in 2017, two neutrons colliding, giving off a gamma ray burst, and also gravitational waves are both observed, which is a really nice tool for testing physics. So there was an observed delay between them. These are graphs from the paper where this was published. So the point is you had a signal of gravitational waves, that's the merger, and then you had electromagnetic waves in the form of a gamma ray burst, and there was some time delay between them. But what you can say from that is that if there's a difference in the speed of a gravitational wave versus the speed of electromagnetic waves, it can't be more than this time delay. So it allows you to do a kind of a bound on any possible difference between the two speeds, which should be the same according to general relativity. So you do a constraint like this. So you basically take the difference in the speed between the gravitational wave and the electromagnetic wave, delta nu. That's supposed to be speed, not frequency. Sorry for the notation. And you divide by v, e, and m. So that's the speed of the electromagnetic wave. So that if this was zero, this would be zero in perfect general relativity. But what this observation allowed physicists to do is place a constraint with an upper bound and a lower bound on this difference in speeds. And so you can calculate the effects from the framework that I was using, and it actually depends on those S-bar coefficients written in a different form, that 4x4 matrix I showed you. And so you can place very stringent bounds on those coefficients, and those were published in this paper about 6 years ago. So this is the coefficients here, those S-bar coefficients, and there's a lower bound and an upper bound, and these are on the order of 10 to the minus 15. So I showed you before the lunar laser ranging results was like 10 to the minus 11, 10 to the minus 12. So this outdoes the lunar laser ranging results by at least 4 or 5 orders of magnitude. So a much more stringent test. But it's in a completely different environment. So compare Earth-Moon to this. So you can do tests in different environments and compare the same quantities. However, we always put an asterisk on this because there were some assumptions about the astrophysics going on here. It's a complicated process. And so I would say, in some ways, the lunar laser ranging result is a little more robust because that's more like a laboratory. But no signal is seen. So I'll wrap things up now. So I talked about this idea of Lorentz symmetry, laws of special relativity, foundation of general relativity, and standard model of particle physics. We're interested in testing Lorentz symmetry in order to find a glimpse of some fundamental theory. And I have projects for undergraduates. So I have Janessa Sloan working on short-range gravity and a new project I didn't get time to talk about, but a radiation project. Also Alex Gard working on that, and Haley Murray working on starting a project with black holes. So there are many recent experiments and observations, but no statistically significant detection of Lorentz violation yet. And if you want more information, I have a website, a Google website, my own research information, and there's actually a general FAQ site on Lorentz violation at this site here. You can pretty much Google it. It should come up. So I'll leave you with this quote by my PhD advisor, Alan Kostelecki, who said, "Nature's beauty may be more subtle than perfect symmetry." That's it. Thank you. I'll take questions.
Do we have any questions today? Especially from students.
So when you were talking about the clock and rod stuff, you had the two different colors, I believe, representing different materials.
Yes.
How are the different materials significant?
I'll explain that. So, like here. Yeah, so the idea is whenever you make a measurement, you have to compare two things. You have to compare one rod against another rod or one clock against another clock. Effectively, that's what you're doing, because when you calibrate, that's what you're doing. You're taking you're using another reference point before you make your measurement. So you're always comparing two things. Okay, so the idea is you could compare two green clocks and rods, but these effects will affect one kind of matter in the same way you don't expect to see anything. When you'll see something is when you compare two different sets of rods and clocks. So that's the idea. So you compare an atomic clock to a pendulum clock or something like that, or compare two different atomic clock based on different atoms that are made with cesium and strontium. So that's why I have two different colors, just represent that you have two different kinds of rods and clocks.
Do we have other questions? Last call for students before Dr. Zanelin. All right.
I'm willing not to ask question if any students has one. Okay. So this is a kind of a out-of-the-box question. The personal interest that I have in these things is also because you can gain insight of some physics that is particularly relevant at the time of the Big Bang. And I saw a number of papers from Penrose and Rovelli that when you get close to the Big Bang, you might actually have to question the concept of time itself. You might reformulate equations where you actually remove the concept of time itself. So is this formulation capable also of testing if the concept of time needs to be revised?
Yeah, so there have been a number of, not a whole lot, but a few works using this framework to study cosmology aspects, particularly inflation. So that's what's been done so far, but probably not directly what you're talking about. I mean, one of the ideas is that in the very, very early universe, when you expect generally you expect a theory of quantum gravity to take over at some point. One possible prediction, if you will, from a theory of quantum gravity is that you might break Lorentz symmetry. So it's one of the motivating factors is that if there's a theory of quantum gravity, it might manifest. You might be able to observe it by looking for Lorentz violation. So there's a lot of stuff you can work on that hasn't been done yet. So still pretty open.
I would like to thank Dr. Bailey again. If any of the students have additional questions or inquiries about research with Dr. Bailey, I am sure that his office door would be open and he would be willing to talk to you. So thanks again. Let's give him a round of applause. As a final reminder, I will be sending out a first announcement today about our capstone presentations for our seniors next week on Tuesday and Wednesday at noon. More pizza coming then, too.